seker maak. Hy sê weer recording. Okay, ons is reg.
Right, everyone. Thanks for joining. It's good to see so many people on the call. So thanks for taking the time out of your calendar to join us. I'll be switching off my camera now, and I'll move to the presentation. Just a bit of admin, as always. If you can keep your mic muted, so to reduce any noise to the rest of the participants, that would be kind. And then let's keep the questions until the end of each presentation. I think you can put them up in the chat. If you got a question, you can type your question in the chat, and then the presenter will be able to see that, and we can handle those questions at the end. It's quite a busy schedule, so I'm gonna start straight away. So I'll switch off my camera, cheers, and then I'll share my screen. Right. And if somebody can just let me know that you can see my screen, then I can start.
Yes, we can see it.
Right, cool. All right, so the idea of today's meeting is because we're not having a user group meeting this year, is to give some updates on the software. Firstly, I think that's the main purpose, and then secondly, and that's my role here first this morning, is to give a bit of an overview on what we saw during this year or the last 7 months, and how things have changed a bit. I think we're working with a new method or new way of working. I don't like the new normal word, but I suppose it's accurate because things will change. How long they will change, we don't know, but let's see. So I'll start off with my presentation, and then we're handing over to Jesse Quick. He'll do some Ansys mechanical update. It's quite difficult for them to do these presentations because these What's New presentations is 100+ slides, and then they had to compact that down to 15 minutes. So it's really updates. So if you have some questions, we can take it offline. You can send an email to each of these guys, or you can keep the questions for the end of the presentation. Right, and then after that, we've got Keith doing the CFD update, and then we'll have Evan doing the electromagnetics update, and then Wynand will do a Rocky one, and then I'll handle the questions. All right, so there's that ugly word again, the new normal. I think I can associate with this a little bit. I'm in a nice, neat shirt today, but I do have a jean at the bottom of it. So I mean, this is how we've been operating. I think most people are working from home. I think research has shown about 80% of people are working from home. So it changed a bit how we worked. A couple of other things has changed as well. We changed the way that we do washing. I must admit, and it was quite a challenge to do all the cooking and the dishes and everything at home for a long period of time. Some of you might have brewed some pineapple beer. Might have been guys that ran out of wine during this time, but it was a challenging time. I think we'll never have a time like this again. I think it was an abrupt change to normal daily living. You really got to know your wife or your husband and your children. That was one of the challenges, I think, to spend so much time together. But I think in the end, the lockdown has revealed a lot, and it's helped also a lot. Just a little bit perspective. This figure is from the 29th of September on the pandemic that we're facing currently. I think the world's reaction was very hectic to this, with reason. It's a serious virus. If you look over history, all the pandemics, I think we're still growing with COVID. We don't know how long this will last. So obviously, I think businesses has changed to adapt to this and make sure that they can still be profitable. Different ways of working, because we don't know how long this will actually take. Some research shows that there's always a recovery from these pandemics and these economic crashes. And there's different ways that this can happen in these L shapes and U shapes and W shapes and V shapes. And it looks like the consensus is that it will take about 2 years to recover out of this. We'll see how it recovers. I see some countries went into a second lockdown period. So that might affect things as well. So there's a lot of uncertainty about this. Hopefully we've got a bit of a L-shaped one or a V-shaped one that that really just flattens things a bit and then it carries on growing again. A bit more specific research for South Africa shows that we haven't had the greatest economic growth over the last couple of years, and they're predicting a bit of a negative growth, 0.5%. Whether this will be the case, we don't know. We'll have to wait and see. But it does state a point of we have to change the way we work to be profitable and to keep on being effective and surviving this whole crisis. And I think that's what most companies has done over the last couple of months. Unfortunately, some companies has taken pay cuts to still keep all the employees. Some companies closed down, unfortunately, which opens up other opportunities again. So it will be an interesting 2 years coming, I think, for South Africa. And then the other thing that changed for me tremendously is I'm a sales guy, so interaction with people is kind of my food every day. And the social distancing impacted that a lot. I think the first time we all got back at the office for Spring Day Braai, we spent a lot of time just chatting and interacting with each other socially again. So I think it's something we miss. Luckily, we've got online. Imagine we didn't have any internet or anything during a pandemic like this and lockdowns. Can you imagine what life would have been and how depressed people would have been? I think we are made to interact with people. So that's why we have these online sessions, luckily, and we can interact with each other. Things that we've seen from our clients mostly is a new way to work. There's about 80% of people working from home from this report. The cool thing for me of working from home was that there were no traffic. I drive an hour to work every morning, an hour back. And then when I see it's 2 clients, there's at least 3 hours on the road. So that's 5 extra hours a day. So I think I was more productive. I had more meetings a day. Some days I had 6 or 8 meetings just because I didn't have to drive all this way on the roads and there's traffic and stress. I think we are less stressed as well by working from home. It depends what you're doing. We saw a lot more meetings. A meeting was very easy to arrange and people would allow you some of their time if it was a quick Teams meeting like you guys today. So we appreciate that. I think that increased communication between departments, especially. We had some meetings with clients where there were different departments present in that meeting, and for the first time they really started talking to each other about the different aspects of some designs. So I think it increased communication in most cases. We saw uptake of cloud-based services in computing. People were working remotely, so they didn't have access to some servers or solvers at work, so they had to work remotely. Some of the cloud computing was utilized, and there was a lot more collaboration. We had very cool meetings with departments and department heads down to the users, which I think was a very cool thing out of this COVID crisis. The second thing we saw a lot is we got some cool software requests of people who want to do interesting things. So I think this time also, because there was in some industries there were a lot of time to kind of restructure and rethink the goals and the visions and where they want to go to. There were a lot of new ideas, and that was good for us. So we had very cool projects that we provided support on, and people are definitely innovative in their thinking and how to improve their businesses, how to look at different simulation solutions to replace some testing, prototyping, etc. We also saw the simulation complexity increase. The kind of technical support we got was a bit more advanced in most cases. I think those simulations that has been lying in a cupboard for a long time started coming out and people started using this. In general, I think we get increased complexity in simulation over the years as people are getting more advanced using the software. And then obviously there were still a lot of cloud-based computing and licensing going on of people who wanted to get new guys to use the software. Some people employed new guys. They wanted some access to the software. The downside of what we saw, well, it's actually an upside for us as well, but was the uncertainty of this time. There's definitely economic uncertainty, so investment in new technology and tools was a bit lower than usually. I had some POs cancelled after being sent due to the uncertainty of this lockdown and when it's going to happen again, etc. There were a lot of critical issues with cross-border work, etc. So we felt that definitely. The interesting thing, though, is that we managed to get more than 98% of our renewal rate going. So I thank every single customer on this call for still supporting us. I think it shows value in the technology and in the software. It shows that people are seeing value in our software, I would like to believe. And that really helped us to keep our team and pay our salaries and go forward. I think we are right, so thanks for that. It's also a very indicative gesture to see how this technology is getting more accepted. We had a lot of meetings with senior design engineers and engineers that's not used to simulation, which we've never spoken to before, and they started to believe the results we're getting from simulation. They wanted to understand more. There were always a deeper dive into the technology after these meetings. And then also we saw an increase in technical support for both Ansys and Rocky, which means people are using it more. They are making more sure of their designs before they're getting produced, because it was more difficult to test designs. And then the other trend we saw is we definitely saw an increase in users. We had online training courses. So we couldn't have training courses at the office, so we had online training courses. Instead of having 4 to 6 people, we could have like 8 to 12 people, have 2 instructors on the training course. So that was very cool. We had an academic online training course where there were more than 300 people registered for this. We were quite worried in the beginning. It worked out very well. It was a huge session. So there was a lot of large adoption there. And then there was a lot of knowledge transfer, I think, that happened through support and training, where we did specific training for some companies on their specific application to kind of dissect their design. And we also saw that simulation became part of the design process more than before. I think the South African thing always with simulation is people want FEM, DEM, and CFD software once something doesn't work or once something is broken. And that has changed, where people are starting to do really a lot of simulation before prototypes are being built. And then our attendance in these online workshops has increased rapidly. I mean, we really have wonderful feedback on these sessions, and I think they are productive. You don't have to drive somewhere. You don't have to go and sit in a training room and take off some time from work. It's literally the hour that you spend. I just want to mention we've got 2. We've got this series we're launching called Learn a New Engineering Skill. And on the 14th of October, that's next week, we've got a free discrete element modeling online training course. And you will get a 30-day evaluation license after attending that. So that's one skill. If you're interested for that, you can send an email to info@qfinsoft.co.za. And then the second one will be FEA CFD simulation workshop through Ansys Discovery. And that will happen on the 21st of October. So you're welcome to register for those, learn something new if you want to look at the software, see what it does. Ansys Discovery is really taken leaps and bounds to what it is today. There's actually some meshing available now with it as well. It's not just voodoo, as I called it in the beginning. It's really an awesome tool. I think that's the future of what Ansys wants to do. So let's check that out. All right, I thank you. I think we can move to the other presentations. I didn't see any questions in the chat, so I think we can carry on. Our next presenter is Jesse. Jesse, are you around?
Yes. Okay, let me just turn on my camera so that I can introduce myself to everyone. So hi everyone, I don't think that I've met most of you in person yet, but I'm just going to be giving a overview of what's new in structures in Ansys Mechanical. So I'm going to turn my camera off just to make it a little bit easier to stream. And let's get going with the presentation. Okay, can someone just confirm for me, please, whether or not they can see the presentation?
Yes, perfect, thanks.
Okay, perfect. So, yeah, like Isak said, this is about 260 slides worth of new material that's been added to Ansys Mechanical. So what I'm going to do is I've narrowed it down to quite a lot less, about a fifth of that, and there are some filler slides in between, but I'm just going to run you through the basics and the new improvements, the ones that I think are relevant to you, and we'll just get going on that. So we'll start off with mechanical core. So now with the mechanical core interface, there's been quite a lot of improvements, particularly for the licensing. So with the licensing options, previously you would have to go into your Ansys admin and then select all of your licensing options and move them up or enable and disable them there. Now this has been built into the mechanical interface. So when you open mechanical, you can go into the file options, and right at the bottom there you will be able to manipulate your licensing options over there. So this is just a little bit of a time saver, so you don't have to exit the program. You can just launch it and then control your licensing from there. Then for contacts and trackers, they've added a couple of contact trackers. So this is always useful for monitoring our convergence and for troubleshooting. So they've added a contact pair force convergence norm, a contact pair force criterion, maximum tangential fluid pressure penetration on a contact surface, and then the same thing for a target surface. Then another useful addition is for sub-modeling of thermal analyses. You now don't have to go into Workbench and go and link up all of your systems. Now it's as easy as reading in your results file. So if you know where your results file is, you can go and import your thermal stress, your thermal loads, and you can add that directly into your simulation from mechanical directly, and you don't have to even exit the interface anymore. Now onto the mechanical graphics and post-processing. So this is just a small one, and this also ties into one of my favorite topics, which is scripting. So they've done a lot of work on the scripting console. But now for the post-processing, you can create custom legends with color bars, and you can use these for all of your designs, and you can export the legend and just read it in every time when you run your simulation. So this will allow you to have a very fine control over your legend and the way you display your results. And this is particularly nice for if you would like to keep it consistent for reporting purposes and so on. Now onto linear dynamics. So they've actually made quite a lot of improvements for the linear dynamics and importing external results. So what I'm showing you here is now with Discovery, which Isak mentioned, you'll have a free trial, learn a new engineering skill course that we'll be presenting. All of the simulations that you do within Discovery, you can actually export your results and then bring them in to mechanical for your more refined analyses within this interface. So it's now as easy as just exporting it and then importing it with the ACT app. So that is quite nice. Then onto mechanical, so the MAPDL migration to mechanical. So these are the more solver related and contact related improvements. So one of the ones that are standout for me is the shell to solid contact enhancements. So now mechanical issue a SHSD MAPDL command for you. And what this does is it actually just improves our shell to solid modeling. And this is typically very nice because we like to use a lot of our shell models. And when you use a bonded MPC contact, under the formulation, we can go and change this formulation, and it will go and allow us to change additional settings to improve our solution accuracy. And if you're not exactly sure what that means, then on this slide now, you can see an example where this has been used. So if you look at the top left and top right hand side on the model without the SHSD enhancements, you can see you get these sort of like wavy type of phenomena on the top left and right. And now with the SHSD, we've got a much smoother model, which makes a lot more sense and looks a lot more accurate. Then we also have our quasi-static solution in the static structural analysis. So for the static structural analysis, when you have sort of a static analysis that occurs over a long period of time where it's actually transient. So if you think about maybe you have a load on top of a can and you just keep pushing down and eventually that can's going to start to deform, then you would want to use a quasi-static type of analysis, and this has been integrated directly, so it's very easy to go and turn it on. By default it is off, and you could just easily go and manipulate these settings directly in mechanical. Then loaded area options for pressure and imported pressure. This is quite nice. So now when you are applying a pressure or importing a pressure, this pressure will consider the change in shape of the model as it's been applied. So you can include deformed and initial. So it will either use the deformed area or the initial area. It is scoping the pressure throughout your simulation. Then for cyclic symmetry, when you import tabular loading and you have a cyclic symmetry reading, you could region, you can see exactly what's happening over here. It's going to scope that exact same symmetry to all of your symmetric regions. So that is quite nice. Then one of the other key areas that they're trying to improve a lot is the fracture and smart growth solver. So with the smart growth solver, now we have our mixed mode crack growth support. So just if you look at the visualization over there, what it does is it supports both static and fatigue crack growth, and there's all the equations there for reference. But the mixed crack growth is based on the maximum circumferential stress criterion, and as we can see now, this is becoming more and more important to simulate these types of crack growth phenomenon. And additionally, this has been included within our fatigue model. So there's additional fatigue models, Walker's and Foreman's equation. And then you can also input your own tabular table for data points that you would like to simulate. Then onto the MAPDL sort of enhancements. So let's start off with contact. So as always, it's always nice to give a little animation within the presentation just to show you what we're talking about. So now you can combine all three contact detection methods together. So what this does is it just makes it a little bit more robust to simulate our models and improve our convergence criteria as we are going through the simulation. So this is quite nice, and it enhances the detection methods. Then for bolts preloads, this is a particularly nice one. So we always know that we have to apply preloads to our bolts, and this is particularly important for all different kinds of simulations to increase the effective area that the stress is acting on. So previously, with the pretension 179 model, the elements that we were using, you could see as the bolt rotated, it lost a little bit of the scoping for the initial pretension we applied. But now when we undergo a large deformation or a large rotation, we keep that exact tension and initial deformation as we rotate our model. Then there's just some general contact robustness improvements. So for non-linear simulations where we use MPC contacts, in the previous iterations in 2020 R1, we got divergence within these contact regions, and now they've just improved it so that in 2020 R2 we get a much better convergence performance. And then another one that I quite like is the enhanced displacement convergence check. So initially it will calculate what your displacement should be, and then if you are under that value, you will get a displacement convergence. But now in order to enhance this, what happens is after the initial, it goes and it updates your convergence check for displacement and updates the criterion to give us a better estimate. Then on the solver side, again, there's always improvements that are being made to the solver side. And for this example, we could see the comparison between 2020 R1 and 2020 R2. This is just involving linear contact, but this is something that always is being improved. So at a lower number, of course, it's not as significant, but for your HPC type environments, it is significantly improved. Then a lot of work's been done for structural optimization. So in the structural optimization, they've included new capabilities such as geometric constraints for volume, mass, the center of gravity, and moments of inertia. And this can be scoped to as many bodies as needed. Optimization region to create as many optimization regions as components in the model. So for each component, you can have an optimization region with its own set of manufacturing constraints, and then you can combine these in unique ways for the optimization. And then for the static linear analysis, there's some UDF work with displacement and reaction forces, which is a beta feature, and there are some other beta features, but there's a lot of work being done on the optimization side. And then leading into that, they've also improved our validation. So when you are doing your optimization study for topology optimization, they've now improved the workflow such that when you're done, you can export smooth STLs and use that for a validation study rather than having to go and do a whole lot of cleanup, which you can spend a lot of time on. And then this is also carried over to the lattice type of optimization studies where you can improve the workflow using a similar methodology. Then for explicit dynamics, so one of the nice new features that they've included is smooth particle hydrodynamics. So this is supported for the Alestina and explicit dynamics solvers. You can specify particle objects with a particle mesh method, and then they've just included this in the visualization process. Then Alestina, which is obviously new all around. I just wanted to take out a couple of slides for Alestina to show what's new on that side, but obviously a whole lot is new in the Alestina type of environment. One of the cool ones that I found was the implicit incompressible SPH model. So this allows us to have much larger time steps rather than compared to an explicit model. And this is tailored for weighting type problems. And you can see it looks very interesting over there. Then there is a moments consistent smooth particle Galerkin model. So this is applicable for multiple applications. So I just chose some interesting applications, whether it is manufacturing, defense and civil, automotive, consumer goods, and biomedicals, the most applicable to the industries that our clients are involved in. Then they've also improved the structured ALE bird strike model. So this has just been improved to include some trimming, and this just improves the performance of the model and speeds up our simulations. Then onto rigid body dynamics. So for the rigid body dynamics, they've included friction in nearly all of our joint type models. So previously it was available for translational, cylindrical, and revolute joints. They've now included it in universal, spherical, slot, points on curve joints, and imperfect joints. So now we can model friction for all of those. Then Aqua, we have one or two clients that use Aqua, so this looked quite interesting to me. We now have time domain pressure mapping for our hydrodynamic response to static structural. So now we can map our time domain for our Aqua model pressure in a lot more simplified and automated manner. So when we are mapping everything from our Aqua load map in ACT, we can read in the external surface and the internal pressures. And based on the time frames that we set, we can actually just map it directly, and it will improve our workflow, and it will go and map that onto our static structural system every time. Then for Ansys Shearlock, so this is for all of our electronic simulations, they've improved the workflow from all the way at the beginning from SI wave to IcePack mechanical and Shearlock for our reliability analysis, and just in general the workflow has been improved, and with that they've included the Shearlock directly into the Workbench, so it's been integrated directly into Workbench. So this just simplifies and speeds up the way that we would normally simulate these types of, well, set up these types of problems, and just makes it more familiar to us rather than having to exit the Workbench environment and then read it into Shearlock every time. And then on that note, they've also gone and improved the Shearlock export to IcePack. So this is just integration improvements from mechanical, thermal, all the way to IcePack in the end. So that is effectively the key features that I thought that I should just run through very quickly for the mechanical side of things. So thanks, and I think that's it from my side. If there are questions, I'll address them at the end, and I think it's on to the next presenter, which is Keith, if I'm not mistaken. Thank you.
Yes, thank you, Jesse. I appreciate that. Thanks for squishing all of that into that time slot. So next up is Keith. Keith, you ready?
Yes, I am. Let me get started.
Cool.
All right, so hopefully you can all see my screen. Good morning to you all, and thank you for attending. I'm going to be giving just the updates on the CFD tools that Ansys offers. And again, there is so much that has been released. So I'm just going to try give an overview as best as I can. So we'll start with the meshing workflow. So the first thing is wildcards can be used in automatic selections from any list in your fault-tolerant meshing and your workflow watertight meshing. And the wildcard is preserved in a journal, commands for future execution. Then also there's a slight change to the buttons, the naming of the buttons. So depending on the task that you have done, then the button will show specific information, which makes it more intuitive for the end user. One nice feature is that the local sizing can be applied to a labeled edge. So the edge needs to be labeled in space claim first, and then just in your advanced settings, you can specify in Fluent Mesher, your advanced settings, you specify that you want to use name selections, edges, and then it will apply a specific sizing to that edge. One can now import a surface mesh from an existing mesh or case file, and its flexibility to also selectively remesh specific surfaces rather than everything. It also supports regional specific sizing. So you can specify the maximum cell size and the growth rate in each zone, each region. With the poly and tet, you can specify both max cell and growth rate, where in the poly hex core and the hex core, obviously there's no growth rate, so you can only specify the maximum cell length. Then the poly hex core and the hex core have been extended to solids as well. So it's completely compatible matrix of mesh types and extraction methods for solid regions. Then there's also a continuous prism layers for polys and poly hex core for fluids. So there's a new continuous option for post-improvement method, which will create continuous prisms without stair stepping. And then it's available in fluid regions that use poly and poly hex core for volume fill. Okay, then let's get over to the multi-phase and the DPM. There's a couple new features in there. So the first one is the new streamlined multi-phase workflow. It's just new and intuitive, a lot easier to access the different phases. So it makes setting up a multi-phase case in Fluent significantly easier. Then there is a regime transition for transitional flow. So this is very handy. For Euler, it's typically recommended for interfacial areas smaller than the grid size, and then you can use interfacial tracking if the length scale is larger than the grid scale. Then the new Gen Top or generalized two-phase flow approach. This model starts functioning once the large velocity group has reached a critical volume fraction, and the model works completely with the Eulerian framework, and it predicts the generalized flow very well. Then there's also a filtered two-fluid and EMS subgrid scale model for gas-solid flows. So your normal homogeneous drag models can yield poor results for large-scale fluidized beds. So the new filtered two-fluid model and EMMS drag model are introduced, which account for subgrid scale effects on macroscopic flow, and it makes large-scale fluidized beds simulations much more affordable and predict realistic expansion and hydrodynamics. Then there has been a number of changes to the robustness of the VOF. So the generalized variants of body force weighted pressure interpolation. So there's better convergence, better robustness, and its applicability and addresses limitations of existing body force weighted. Then the hybrid NITA improvements. So the velocity-based instability detector mechanism has been improved. So that helps with the stability of the NITA solver. And then the turbulence damping improvements have been extended to the K-epsilon models, which give better resolution for gradients in the lighter phase. Then a new droplet model breakup model has been added, and that's the Schmiel, and it's going to be implemented both in Fluent and CFX, and it's typically used for gas turbine injection, fuel injection. Very good method to use. Then the high resolution tracking model capabilities. So the capability with DEM is now fully supported feature in high-res tracking, and the capability with moving deforming mesh is now also supported. So that's for the DPM. Okay, then there's some other physics and models that we can talk about. So the first one is the general turbo interface for combustor and turbine stages. So all species models are now available within this, and the frozen rotor and transient rotor stator can use simplex in the segregated pressure-based solver. Then non-equilibrium wet steam can also be modeled. It is important for obviously steam turbine modeling, and it was only available for the density-based solver. Now it's also available for the pressure-based solver. Okay, impedance boundary condition inputs utility. So Fluent requires inputs of complex poles describing frequencies. So the new utility fits the impedance input data based on experimental acoustic material data. Then on the radiation and heat transfer side, Monte Carlo model has been enhanced, so you can specify boundary sources on internal opaque walls, which is very handy, and then additional wall fluxes for post-processing are available. And then, yeah, you can write S2S files in CFF-based .h5 file format, which is very handy. Okay, one thing that has been needed for quite some time is the heat transfer coefficient based on some specific Y plus. So that has been changed. So you can now, the new field variables used for fluid temperature at a specific Y plus value for HTC computation. So you can specify under your user defined preferences, you can define the Y plus that you want to. It is default is 300, but you can change that. So the new post-processing quantities which will be added is the Y plus based on the heat transfer coefficient and the Y plus based on heat transfer reference temperature. And then in the intrinsic fluid structure interaction, there's support for non-conformal interfaces, which will be very useful and allows for more optimized mesh characteristics for flow and structural solutions. Then Grunter material data is also available in Fluent under the MSD license. Okay, then some solver enhancements on Fluent side. So on the HPC side, so sliding mesh enhancement, so you can see the improvements. And then there's also enhanced coupled solver performance. You can see the improvements that have been made. Okay, so on the numeric side, the correct form option for the pressure-based solver, there's improved robustness and a 5% speed up. And as before, the multiple reference pressure formulation is now as default. You can do mesh adaptation for overset meshes, which will improve the mesh connectivity using overset methods. Okay, then on the joint and design tool side, so the joint turbulence equation, so the Gecko generalized K omega turbulence model can be included in the joint sensitivity. So this is very handy because Gecko has tunable parameters and it can optimize your turbulence model specific to your application. Then you can also, in the design tools, you can compare optimized mesh and the reference mesh easily. Then there's also bounded surfaces, which can be applied as a boundary condition. And then simplification of exposed settings for regional conditions. So reorganize different conditions. It's a much simplified region conditioning, especially for the invariant conditions. Then there's extensions of the direct interpolation, supports symmetrical regions and motion condition for both Cartesian and cylindrical coordinates. Then the gradient optimizer improvements. So update the optimization history monitor more frequently. And then there's also a STL export of arbitrary surfaces, including ISO surfaces. Last thing I want to talk about is extensions. So patching can now be done with extensions. So you can patch and initialize a solution with some expressions, should I say. Material property definitions can also be defined using expressions. There is a new diagnostics plottings for expressions as well as material properties. There is also expressions of new functions, so weighted reduction functions like sum or average, and then you can also use the hat instead of 2 stars to do a power. The expression usabilities the GUI has increased and it is a lot easier to use. Okay, and then there's the graphics post-processing. So there's been a few manipulations on the mouse movements and buttons, and it's kind of becoming more uniform throughout the different tools that are available. And then the multiphase boundary conditions consolidated. So there's, instead of multiple separate dialog boxes, you can access the phases using each boundary condition. You can mesh edges now off by default, and you can save scenes. There's a shortcut for saving scenes, and there's new additional color maps available. All right, I think that is enough. It's running out of time. So I would like to thank you for listening, and I hope it was useful. A lot of else has been changed, so start playing around and see what is available. I think it is now Evan to take over. Thank you very much.
Thank you, Keith. That was good. Evan is up next. So if Evan is around.
Can you hear me?
Yes, absolutely. Please go ahead.
Right. Morning, everyone. What we're going to look at now is we've kind of called it the EMAG or electromagnetic products, which kind of lumps a whole bunch of different products together. But I'm really just going to focus on Maxwell and HFSS, which are the two main packages in that category. So Maxwell, while being a general solver for low-frequency applications, one of its major uses is for electric motor design. And there's been a lot of development in Maxwell for that and all the tools related to that, particularly because industry trends are looking for electrification and particularly motors for electric vehicles and that. So there's been a lot of development right from initial analysis, just some sort of quick analyses for 2D models, to looking at the full EM sort of spectrum, looking at all the losses and the detailed electromagnetic analysis, as well as all the thermal applications as well. Okay, trying to do that within Maxwell, as well as coupling with tools like CFD and mechanical for the FEA analysis of that, and then also integrating that with level analysis like Twin Builder, or looking at OptiSlang for some sort of local optimization of the design. And it's really wanted to show the slide here because it's for some particular example of noise, vibration, and harshness, which is quite important for sort of people interacting with the electric motors. There's obviously a lot of integration with mechanical, looking at sort of the acoustics of the engine, the vibration and the noise generated from that. And that's even now being coupled with a VR experience, which is a fairly new sort of product in the Ansys range. And the idea is that if you characterize the full vibration frequencies of your motor, you can actually generate a sound file for that motor. So I'm not sure if you guys can hear it, but you can actually hear the motor whine as it revs up.
We can't hear that even.
You can't hear it, okay. But believe me when I say you can actually hear the motor whining as it spools up there. So that's quite a nice integration to really get the full analysis of the electric motor. And you can see there on the left, we talk about a product called MotorCAD. For those who aren't familiar with it, it's also been released within the last year. It's kind of like RM Expert for those who know a bit of RM Expert, except that it adds a lot more features to it. So obviously it's got a template-driven 2D analysis with the full FEA solutions for that. But then it also incorporates other physics like thermal analysis and things like that, and sort of mechanical stresses, so that you can not only just do an electromagnetic study of your motor, but you can look at some of the other physics very quickly. So before you've gone and done a full detailed analysis, you can actually just throw out a couple of different designs and kind of hone in onto your optimum design much quicker. Okay, so that's a new standalone application for MotorCAD, and it links with all the other physics as well to do a more detailed analysis later down the workflow. Okay, then looking at some of the Maxwell, so bringing in for RM Expert, you can actually bring in a custom CAD geometry. Okay, so it's not just working with the UDPs in RM Expert, but you can actually bring in CAD files for the different components in the motor, so you can get slightly more detailed design or more custom design for your application. What's really quite handy is looking at ways to streamline the workflow setup within your motor analysis. Typically, you're going to have some sort of periodic geometry, and because you don't want to solve the full motor shape, because that's going to take very long. So if you can break it up into little slivers, that will speed it up. But then also setting up the model to create that little sliver is also sometimes a bit of time consuming or painful. So the idea is that you can set up your model on the full geometry, and then you can actually get the Maxwell to automatically slice it up and solve it for you. Okay, so it just saves you a little bit of time on the setup there. Then the new meshing option. So this is an enhancement of the existing tile mesher. So this is the tile flex mesher, and it builds on the existing meshing technology and just gives a bit more robust, especially for more dirty and more tricky CAD geometries. And it just sort of helps you get a much more efficient use of the mesh. And then what's also quite nice is using, sorry, I'm just going to place a pointer here. So using this dynamic surface resolution setting, so that basically it just groups the mesh around complex geometry like high curvature, but then gives you less mesh where the geometry is much more flatter and simpler. Okay, then also in the previous release earlier this year, we brought in a new A-PHY solver. Okay, so this is an additional solver to your magneto or development of things like your magneto static solvers and things like that. But the idea is that this is particularly used for things like bus bars and IGBTs and flat PCB boards and things like that. So particularly your high power applications, this is a very fast and efficient solver for that. Then obviously with all the concentration on multi-physics, it's about trying to simplify the workflows and bring everything together. So you can actually now bring elements of a mechanical FEA analysis into the electronics desktop. So here we can look at either a modal simulation, just to look at the basic vibration response of the casing and geometry, as well as a thermal analysis. And you can do that all within the electronic desktop. You're not having to export or go back out and into mechanical to do all of that. Okay, so for some simplistic analysis, at least for now, the workflow has been much more simplified. Then something that's been a lot of sort of fanfare over the last sort of year or so is this idea of grantor materials libraries that have been added to all the solvers. So I think it was end of last year, the last release last year, some initial materials were added to the Maxwell database, but this database has been extended. So now you're getting even 500 plus material data from different manufacturers. So it's actually manufacturer specific, and it has all the magnetic sort of material properties that you would need to do complex physics within Maxwell. Okay, so it's putting all that information there ready for you to use. And then there's also been some other enhancements for materials. So looking at things like temperature dependency, so you can setting up your pH curves, having different curves based on temperature, and the solver will interpolate between them. And then also things like your having anisotropic core loss coefficients and temperature-dependent core loss coefficients. Okay, so there's been a lot of development there for a little bit more sort of realism and accuracy on the material side. Then on the performance side, about a year ago, Maxwell was released, or the compatibility with Ansys Cloud was released. And since then, there's been a lot of development, particularly using things like the time decomposition method, and you'll see some other advancements with the main decomposition method. You can really leverage the large scale computing power of the cluster and really drop your simulation time. so instead of waiting half a day, you can do it over lunch and sort of get on with your work. Okay, so within the solvers, there's been MPI support for the domain decomposition method for the magnetostatic solution or solver type that wasn't available before. So this can allow you to now run distributed memory over different nodes and get run much bigger problems and hopefully get a good speed improvement there. Then on the flip side, for the 2D transient solver, we now have OpenMP support. So using the shared memory option, which can benefit some of the larger problems for the 2D models. And then also some GPU support for frequency sweeps. So GPUs can't be used for all the solvers within Maxwell, but for certain applications it can be quite handy. So now we've added a bit more support for that. All right, so now we're focusing on HFSS for the high frequency applications. Looking firstly at HFSS 3D, so this is sort of HFSS product. So again, lots of development for requests from industry to look at large antenna arrays. Okay, so there's been a lot of development and tools focused around simulating these kind of arrays. So firstly, well, the 3D components that have been available within Maxwell and HFSS are now used to build up an array. So in this sense, we take our array and build it up in smaller pieces, little regular repeated pieces, and these will individually be 3D components. We can create our phased array pattern based on these components. So you can see we've now designed the layout, and HFSS will bring in all these different 3D components and construct our full phased array. Okay, so that's been a lot of work there to simplify the workflow. This is typically a lot of emphasis on the development with 5G and arrays for that application. And then I guess further, just what's not mentioned here is this also has been allowed to be meshed in parallel as well. So these individual elements can be meshed separately, also speeding up that process as well. Then following on the 5G thread, there's obviously a lot of emphasis around the world to develop 5G products. So there are some little toolkits and wizards within HFSS now to create different components, standard parameterized components. You put in your details and it'll generate the components for you. And then also that sort of sets up your post-processing as well. So a lot of your features are, or the things you're interested in will be, or the information will be generated for you automatically as part of the solution process. Then looking at the iterative solver, so what maybe some people don't know is HFSS has two solvers. One is the direct coupled solver, and the other one is the iterative solver. By default, we work on the direct solver because it's generally being quicker and more efficient. We typically only use the iterative solver when we want to do, we maybe had a limit on memory because it uses a lot less memory, but obviously it takes a bit longer as a result. But there's been a lot of development in this now, making that the iterative solver actually faster than the direct solver in certain applications. So you get a memory benefit as well as a speed benefit. So certainly worth checking this out for your application. It might not give the speed up for all applications, so it is worth just checking out. Then obviously with more focus on EMI and EMC problems and trying to analyze designs before they get put into production, there's been a lot of sort of defined templates added to HFSS. So as I've spoken about 3D components, so these are our library components that you can pull into your analysis, and they've been all set up and defined already for your particular application, or even just full examples. So it's not just a component, it's a full model setup and geometry and everything. Basically a ready to run example can also be brought in from the standard library. So maybe it'll speed up the setup of your model, or at least just help you understand how to get the best out of your EMI or EMC types simulation. And then further on to that, in my EMC, we're looking at shell elements. Okay, so this is now, maybe you don't want to, for example, this car model here, you don't want to model all the detail of the car. You just want it as a shell body, so you can get a general idea of its influence on the components. So there's just been some sort of additions or enhancements in this area just to make it more efficient to solve a large-scale problem like this. Okay, then now looking at SPR+. So this is part of HFSS that looks at the large-scale systems, particularly the installed locations of antennae. So creeping wave has been a technology we've added over the last sort of year or two, just to help get more accuracy when looking at things like radar cross-section applications and things like that. So there's been a lot of emphasis on development on the target side, but now we're also looking on the source side, where the antenna is placed, just to give the sort of local near field a little bit more accuracy and fidelity there. And there's just some examples here. So, well, this is not only the creeping wave, but this is in general adding some near field analysis detail for SPR+, because typically SPR+ you use more for large far field analysis, but obviously you want to see what is the performance locally. So in this case here, we've got a 1 gigahertz monopole antenna set up on a frigate. We can see the general field as per normal, but we can also now analyze more locally what is the effect of the structure around that antenna. There's just some more examples, different modes there. Okay, and then a new, so I suppose, physics edition, if we want to think of it like that, for multi-paction. So this is particularly for space applications where you've got high power density through your components, and you get the breakdown, electronic breakdown of the material. And we now add the physics to actually calculate the reduction in performance based on multi-paction. Okay, so you can also set it up either manually or even automatically, where it will find what is the limit of the operating point before breakdown and degradation of the performance goes down, and set various limits there for that. So maybe you're okay with running in your degraded power area, or maybe you want to stop at the threshold. Okay, now looking at HFSS 3D layout. So this is a version of HFSS looking particularly at things like PCB boards, flat planar structures. So this is kind of a bit of overlap with SI wave. There's now support's been added for an automatic setup. Okay, so this is it will pick all the best settings in terms of accuracy and meshing and all of that. It'll pick all of that for you based on your inputs you've put in and your frequency sweeps. So this speeds up a little bit the workflow for the user and often gives you a much better result much more quickly. You can still go to the advanced mode, which is the old manual method, if you do want to use that. Also for setting up things like pad stacks, you can now draw them within HFSS and just assign them or create these primitives, the geometry primitives, into pad stacks that don't have to be imported from an external source. Then looking at circuit elements, so you'd use some sort of S-parameter or RLC type specification for components or circuit elements that you don't actually want to model in full detail, but now you can also describe them with some sort of a circuit model as well. So something a little bit more complex or customizable for different applications. So this is all handled through the GUI, new GUI components here. All right, then just some sort of highlights for the desktop side of things. I really just want to highlight this topic here that support for Insight has been added now to HFSS. So for those who don't know, Insight's a fairly new post-processing application within Ansys. So the idea is it can bring in information from all the different Ansys products, and it can allow you to do lots of powerful post-processing, make really good-looking graphics, high-quality graphics. You know, so it's a little step above some of the basic offerings in some of the packages. So we can now export HFSS data to Insight, and you can sort of make really good-looking pictures for your reports. And then lastly, another module that's been added in sort of within the HFSS range, but is also a standalone product, is this EMA 3D cable. So this is for people who are looking at doing, you know, cabling harnesses within large vehicles like cars or airplanes or something like that. You know, where you don't actually want to model the exact detail of each individual cable. You just want to look at the harness as a whole. So what EMA 3D is it's based in SpaceClaim. So you use SpaceClaim to set up the geometry of the vehicle, the geometry of the wiring harness, and then you specify all the properties of the harness, like what are all the different cables that are running within there, the sizes, thicknesses, shielding, all of that. And then it runs a sort of essentially an analytical model just to see how the field will affect the performance of the cable harness, and then you can post-process that all within SpaceClaim as well. Okay, so this is not the full FEA accuracy that you would see within HFSS, but for a large-scale system like a vehicle, you know, on a big scale, it can be quite efficient and accurate enough for your application. Okay, so this is sort of a new addition to the family as well. Right, that's it from my side. So back over to you, Isak.
Thanks, Evan. That was good. It's interesting to see how Ansys is expanding into other physics as well. I like that virtual reality. We should actually post a link to all the attendees of that engine, how it simulated that. Yeah. All right, last up, we're running a bit late. I apologize. You can see there's so much to say. Last up is Wynand with the Rocky update. Are you there, Wynand? You might be muted.
Yes, thank you. I was muted. Thanks a lot, Isak. Hi, yes, I'm here, Isak. I'm ready to go. So I'm going to jump in. Hi, everyone. Just turning my camera on here for a moment, just in case you don't know me or you haven't met me, just to give you a face to put with the voice. Okay, then I'm going to switch that off and get over to some more interesting presentation, and that's the one for the Rocky update. Okay, so I'm going to jump in, and if anyone can't hear me properly or so forth, please just feel free to let me know. I am going to jump in before we get to the newest version of Rocky. I'm just going to jump in with a short couple of slides of features that were added in the Rocky 4.3 version that was released at the end of last year, but it's because it's been a while since we've spoken, and I just want to highlight a couple of nice big features from 4.3 before we get into the 4.4 release, which released a couple of weeks ago. That also has quite a big change or two, but I'm going to try and keep it as short as possible, and hopefully we can get through it before the end of our session. Okay, so to jump in 4.3, there were a couple of big features that I just want to highlight, as I mentioned. So the first one is the coupling with Fluent that allows for a single phase in Fluent and the representation of the particles as a porous media, instead of representing the particles as a separate Euler phase as it used to be in the previous versions. So this way of two-way coupling with Fluent will just speed up the simulation time immensely from a CV point of view, because now you just have a single phase and porous media, and you can still get accurate and complex results as shown in the simulation on the right-hand side here. Do take into account that if you want to have multiple fluid phases, you would still need to do an Euler model, but you can use this new model if there's only a single fluid phase. So let's say there's only water and particles, for instance, then you could do the porous media method. But if there was water, air, and particles, then, for instance, you would need to still do the Euler approach. Okay. Then another feature that they did add in 4.3 is this liquid bridge model, which is a more automatic way of doing adhesion force inside of Rocky. It is slightly more expensive from a solving point of view than the normal adhesion models where you just define your adhesion factors, But what it can allow is for dry particles to become wet as they interact with the wet particles. So it gives you that additional functionality. However, if that is not something that you specifically need, if all your particles simply need to have a adhesion force, then it makes in some cases still more sense to use the normal adhesion models just because it's solved faster. But if you have to have transfer of adhesion between particles, then this new model is definitely going to allow you to do that. Okay, and then probably one of the bigger additions of the 4.3 was the fact that they had added volume filling, right? So previously you had to have like an inlet, and then you had to spend a bit of time at the start of your simulation to fill volumes manually, like just shown here. But in 4.3, they did add the volume fill, which allows you to initialize your system already full of particles. And as they show you, this is just an example, but something like this could have taken 21 hours just for the filling process. Now that can happen automatically in more or less 10 minutes, right? And this can be done with spherical particles as well as shaped particles inside of Rocky at the moment. So you can fill just a box volume, or you can have a specific geometry be filled to a certain level and so forth. So you can actually base the volume filling off of geometry boundaries as well. Okay. And then another nice feature that was added in 4.3 was the fact that the contacts between particles and the contacts between the particles and the boundaries has been added as a separate entity in the tree. So you can post-process contacts separately from Rocky 4.3 onwards. You can visualize where contacts are happening, and you can also extract information for the context, such as contact forces and so forth. And this can also be isolated to certain particle groups or to certain boundaries and so forth. So you can, for instance, isolate all the contacts on a single boundary only to see what happened with the contacts on that specific boundary and so on. Okay, so there's just a lot more post-processing capabilities from a because of this feature. Okay, so those were the major features from 4.3 I just wanted to highlight. So let's jump into 4.4, which is the version that was released a couple of weeks ago. So firstly, there's just a couple of very nice quality of life features. And the first one is the fact that you can now, instead of using an inlet or a volume fill, you can read in a CSV file to actually position particles in space, instead of just chucking them into your simulation at a specific point. So your CSV file can have a position, X, Y, and Z location where the particle should be initiated. You can define things such as the rotation of that particle, as well as at what time it should be added to your simulation, and velocities and so forth. So you can actually physically go and place with the CSV file particles at X, Y, and Z locations in space. And this allows us to build up complex particle interactions. So for instance, if we want to simulate a chain, we can define a CSV file that initiate these particles already interlinked. And then when they hang under gravity, they will actually interact with each other, and we can get accurate type chain type simulations. This was something that you could do previously with a bit of a hack if you positioned volume fills at specific locations and got each volume fill to only drop in one particle. But you can already imagine it gets quite complex and it takes quite a bit of time. Now you can simply just type up an Excel file and read that into Rocky, and it will initiate your chain for you. And you can really do some very complex particle interactions because you can now go and manually decide where all those particles are placed in space. Okay, then another feature is they added the capability of, sorry, this video is it struggles a bit. I'm just going to play it outside of presenter mode for you guys. You should be able to see it now. You can now manually define the center of mass and moments of inertia for a particle. So you can offset particles' centers of mass and inertia if you want to see the effect that would have on something like this, for instance. So here we have the same particle shape, which is just a bottle filled to a certain extent. But based on the fill, we are changing for some of these bottles the location of the centroid of mass, so that we can see the effect that'll have as it moves through our system. Yeah, let's just jump back into presenter mode here, get the laser back. Okay, and then they have also added the cyclic periodic domain option. So currently in the previous versions, you could do translational periodicity for your boundaries that we used a lot for mills, for instance. But in the new version, you can have a cyclic region. So in this example, for instance, for this model here, they only physically modeled a 90 degree slice, so just a pi slice. And then we just tell it that everything leaving one boundary should just enter the other boundary based on a rotational coordinate system. And that will definitely speed up your system a lot, as in this example, for instance, by modeling only 90 degrees, we're almost 4 times as fast, right? Not exactly, because there's a bit of overheads for the calculations of where the particles should be added back to your system, but this can just save you an immense amount of time for these cylindrical rotational type of systems. Okay, and then the big addition for 4.4 is the fact that they have finally included a solver API. So by using C# little modules or scripting files, the users can now actually change what is happening inside of the solver. Okay, previously we could use Python to change pre-processing and post-processing operations or automate that, which we can still do. But now by using C++, we can actually affect the solver itself. So we can change the calculations that the solver physically does by writing C++ modules for Rocky. Currently, the solver API is focused on applying different options to the particles themselves. So we can affect currently the body forces that particles experience. We can change the contact force module. We can change the joint force model for flexible particles, and we can also change the size and mass of particles in our simulation based on certain parameters, as well as change how heat is transferred to the particles. So it's very particle focused at the moment, but on the roadmap for future releases is to also allow API access to things such as your motion frames. So you can change your motion frames and make motion frames functions of other simulation variables and so forth as well. But for now, it's focused on the particles. When you do write the module and you add it to your system, the inputs that you define in your C++ code will actually be exposed as variables in the Rocky interface that you can define the values for. So it's fully integrated into the interface once you compile and add your module to Rocky. And your post-processing values that you define inside of your module will also be able to post-process using the standard post-processing algorithms in Rocky, right? So if you have custom outputs, you'll be able to see them when you want to do contour plots, and you'll also be able to create your custom user processes based on the custom outputs that you define in your C++ modules. Okay, so just to give you a couple of ideas or examples of how these can be used. In this first example, we have a model in which we are changing the adhesion force in our system over time based on some value. Okay, so we have a adhesion force that we are adding manually through the C++ module that is increasing as simulation time increases exponentially. Okay, so we can have, for instance, represent something like this, where heat being added to our system would make the particles more adhesive and so forth. So you can do custom things like that. For our flexible particles, as I mentioned, we can affect the joint forces. So when Rocky does flexible fibers or shells, it actually has little elements that it connects together with joints, and you can affect these joint forces now with the solver API. An example of where that was used, as in this case, we have a little wheel moving over a carpet. Currently, by default, these fibers are isotropic, so you can see the effect of that. But by using the scripting API, we can change the stiffnesses in different directions. So we can make anisotropic fibers and affect how our simulation will respond to something such as a wheel moving over a carpet, for instance, which is not necessarily going to be very valuable in the mining industry, but it still is quite interesting to look at and opens up a lot of different options for the use of Rocky. Okay, then one of the very big features that I think we'll see the most use is the fact that along with these solver API that we have now, you can also import point clouds which contain loading information. Okay, so you can import point clouds that have information on electromagnetic fields as well as information on flow fields. And then by using the solver API, you can have the particles be affected by these fields based on certain body forces that you can define as a function of these fields. So to give you an example of where that has been used, in this example, we have particles flowing through a system, and these are magnets that are being switched on and off during the simulation time. So you can see how the magnet actually affects our particles. How that would happen in the background is we would generate a point cloud for the electromagnetic field in something such as Maxwell, for instance. You'd import that field, and then you would write a solver API that says, when a particle passes through that field, it experiences X amount of body force based on the electromagnetic field. And you can actually then get magnetism into these systems and see how your particles will be affected by magnetic fields. So this is something that people have been asking for a while, and having that functionality, I think, will definitely add a lot of value. And it, again, will just allow us to do much more interesting simulations. Okay, so obviously when working with a solver API like this, it's going to be in C++ code, so it's going to be relatively complex, but ESSS have made available a lot of resources to get users going and to allow them to get up to speed with the solver API. So there is, I think, one of the best available resources will be the code examples that there will be available within the documentation of Rocky. In many of these cases, you will never have to code something completely from scratch, right? You'll get something that they've already created, a little example code, and just change the values to get it to do what you want it to do. So in much the same way as we do for Fluent UDFs and so forth. And there's also a reference guide that tells you all the functions and codes that can be used in the API. And ESSS will also be creating workshops, little tutorials that you can work through to give you a better idea of how that works. Okay, so with this solver API and the Python scripting API that we've already had in the past, this really gives us the opportunity to modify Rocky to a very large extent and automate it and do very complex simulations. So I definitely am very excited to see all the things that can be done with this API, as well as how they extend this API in the future. Okay, so that's going to be it from me. Thanks a lot for your time and allowing me a bit of your day to do a quick presentation on this. So Isak, I think we are back to you now, right?
Yes, thank you, Wynand. That was good. All right, I see we still have some people left in the meeting. So thank you very much for attending. If you have any questions, the time is now. You can also send an email to each of the individual guys if you have any specific questions. If not, then I think that concludes the meeting. Thank you very much for your time. Thanks for the presentations by Wynand and Evan, Jesse and Keith. And stay safe. We'll see you again.
Cheers. Thank you.
Cheers. Thanks.